Yo. Thank you, Titus. You're welcome to today's talk series. We are honored to have Olayemi Adeyemi. She's going to give a talk titled Mathematical Modeling and Microphysics of Snow Distribution. I don't know if Yemi, you're in position to share your slides. Please proceed.
Yemi, are you here? Hello, Yemi.
Yemi, please unmute and.
Sorry. Yeah.
Yeah, you can start. You have 25 minutes.
Yeah. I have 30 minutes. Okay. Thank you. So today I'll be talking to you all about mathematical modeling and microphysics of snow distribution. And here is my outline for the talk. How I introduced the cryosphere, snow, presents my seed papers, then what snow cover entails, then the snow transport modes. And I'll talk about the microphysics involved. In the microphysics involved, I'll speak about the suspension modeling, what suspension is, and I'll just show you one or two things about my computing artifact, then give the model description, give some examples of snow models, give the limitations of snow models, and also just present some open questions. So the cryosphere, we know the Earth is comprises of different areas, like different layers. There is the geosphere, there is biosphere, there is lithosphere, there is cryosphere, and so on. So for my sentences and whole, I was, just like I've earlier said, that I was talking about the modeling of snow, like distribution of snow. So, and the snow is found in the cryosphere. So in the cryosphere, we have other parts of, not only the snow, we have the sea highs, we have oceans, we have other good stuff like this. But that the cryosphere is that part of the Earth where it snows. There's a part of here where the snow and the ice covers. So what is the snow? You know, the snow is not just a new topic to everyone here. Okay, even if we have not like seen the snow, like seen it before or like touched it, at least I know we would have like seen it in movies, read about it, and we know that it's kind of a whitish kind of stuff. But here I have a better definition for you. It says it's a solid precipitation in form of minute crystals at temperatures below 0 degrees. So it tells us that snow is actually like formed at very, very low temperature. So you cannot have like a very hot or sunny day and tell that you have snow now. So, and also snow is like seasonal. It's actually happens like in a specific season of the year. Like it's although most times it happens in the summer, and some of the residues can still be seen in the spring, but majorly snow falls in the summer. In the winter, sorry. So it says snow is formed when temperatures are low and there is moisture in the atmosphere in the form of tiny ice crystal. So for snow to be formed, the temperature must be low, then there should be moisture in the atmosphere. So you might be wondering why snow, because anytime it snows, everything just gets cold. There aren't like productive stuffs going on like that. Like people can't really move about as before. But actually, snow is kind of very useful for in the climate. It actually regulates the planet's temperature due to its reflectability. Like it's kind of when snow like falls to the ground and sunlight like rays on it, it's kind of reflects all the almost like 80 to 90% of the sunlight that is hitting its surface. And in that way, it kind of regulates the planet's temperature. And also it acts as an insulating blanket that it prevents heat and moisture from escaping to the atmosphere, thereby reducing the risk of wildfire. So here are the research papers that I used. Most of it was just talking about snow distribution, accumulation, was talking about the microphysics involved with snow, and some of it were just talking about, let's say, the areas where snow should be modeled. Then now we have the term snow cover, because when you look, people don't actually like call it snow everywhere, because when they want to talk about snow, they just don't call snow as it is. They talk about it in terms of its depth and its area. So for you to have a better understanding of what snow, like description of snow, so the term snow cover actually is being used. So the snow cover term describes the blanket of snow that covers the ground. And this snow cover is actually also very interesting in the sense that it gives like the snow area in the area which snow covers every like yearly. You can use like, let's say for instance, now you want to look for like a parameter, or when you have a snow data, and you want to like get like the parameter that talks about the snow. One of the parameters you look at is like the snow cover. So that's why like the snow cover is very, very important. Like it's a parameter that describes the snow in terms of its depth and its area. And from research, you see that in terms of area, the snow cover, like it takes about 31% of the land area annually, wherever, because the snow just falls on the ground during winter like rain. So it takes over at least 31% of the land area. So it says it's an integral piece and driver of the Earth's climate, just like we've earlier established that the snow is actually very good for regulating temperature and all of that. So the snow cover too, just the blanket of snow, is also like an integral piece of the Earth's climate. So in the snow, like in the snow cover, there's an energy balance, because in this snow park, we used to have something like this. Okay, we know now it is fall, like it is fall, and we have dry leaves on the floor and all of that. So when it snows, snow doesn't just like scrape off those things that we have already, but it falls on it. So while it falls on it, there's like an energy, like an internal energy that is actually like that takes place inside. That is an energy that it takes, because we know energy is the ability to do work. So it's an energy needed for the snow to be together, like to form together. And it is like described with this equation minus dh dt, and we have all, it's on meaning that the minus dh dt is the snowpack internal energy. We have we have qs, we have ql, we have qh, that it tells us that there's a part of the turbulence flux of sensible heat, there is radiation that works with it and all of that. So in the snow cover, there is energy. So also in 1995, in one of the papers that I read, there's this man, Matthew Storm, he and his colleague actually like classified seasonal snow covers, just like I started earlier established, like snow actually happens most time, like it's in the winter. So it's a season. You can't just see it every time. You see it in a specific season. So because of this, they call it seasonal snow cover. And also, and these classes were actually based on the compositional characteristics, the texture, the snow layers, the thickness, the hardness, the wetness, like the density of the snow. So and these classes include tundra, taiga, alpine, maritime, prairie, and ephemeral. So this classes actually like sounds weird and like, oh, I don't know what this is, but these are just like talking about the kind of locations that you find like the tundra is now talking about like tree-like areas in the Arctic, while this taiga is talking about like places like with the rainforest, that where it snows there. And the alpine was just talking about places like had a mountainous area, that places filled with mountains. So it's not as if it is something like, so the classification that he actually was like the kind of snow that the snow cover that he have in those areas that based on the topography and based like on the height. So we see snowfall is an essential component of solid precipitation in the alpine region. It's a very, very important part of it. And snow is eroded in areas exposed to strong wind and is deposited in areas sheltered from the wind. So now I've spoken about, okay, that there is snow cover, now that we have areas. So now let's talk about this transport mode. Okay, so how do we transport this snow from like one place to the other? Like how does the snow move? Don't forget that I said I will talk about like snow modeling, the microphysics, like and the distribution of snow. So you should know that for distribution to happen, like there's a transportation that occurred. So here in this diagram, we have the precipitation like falling down. We have the solar input. I already established that snow also has a reflectability attribute, that is when sun falls on it, like it's reflected back. Then we have sublimation, erosion, deposition, topography, and all. So we have three based on this 19 in Kosugi's work. He actually like described the three main transport modes of snow, that we have repetition, we have sortation, we have turbulent suspension. The repetition is just like blowing of, let's say, blowing of things, rolling over of particles that are on the snow, just like blow it off like with air or wind, just blows it off. While sortation and suspension are like the two major transport mode of snow. And this sortation actually, you see it corresponds to transport of snow crystals in a layer close to the ground. So it's the part of that corresponds to the layer. If you look at this diagram, you will see it's close to, this is the topography, like the hill type on the topography. Then this sortation area layer, it's closer to the surface. Then we have the turbulent suspension right on the top of the sortation. So it says so turbulent suspension occurs in the atmosphere above the sortation layer, where turbulent eddy transports snow grains without contact with the surface. So you see from here that in this turbulent suspension, there is no movement of snow on the surface. It's like the sortation layer actually like makes a background, while the turbulent suspension actually like works on it. So there is this wind field, there is erosion and disposition. So disposition and erosion just like ways like when it is being transported, like the motion, like the way it's, when let's say there is rainfall, flood, and you see that the water just moving like with like erosion, like just move very fast. So that's just like the deposits snow from one layer to the other. And the wind field is a very important part of this, because we need wind for snow to move, for snow to be transported from one position to the other. And to drive the snow transport, there is a wind field that is needed. And this wind field could just be obtained by, let's say, interpolation of wind speed and direction based on the topography, or we even use some atmospheric models that are in charge of this wind field. So it's not something out of the ordinary, it's just the understanding of what really happens, like snow being transported from one position to the other. So now that we already established like snow is being transported from one point to the other at the end, then we have like the physics of what happens. Like, okay, yeah, we know that snow moves from one place to the other. It could be suspension, it could be sortation. So what are the microphysics involved? So this microphysics of snow just entails like talking about the microscopic part of like explaining the phenomena of snow into little details, like the microscopic scale. And based on previous research, we find that we have two ways that we can incorporate this microphysics into numerical models. So it could be a bin solving model parameterization, or it could be a bulk microphysical parameterization. So in most of the studies out there, it's the bulk microphysical parameterization that we use because it is actually cheaper in terms of computer time and memory, and it's not costly. Unlike the being cloud model, it's actually very costly. It takes a lot of time. And you know what we want is efficiency. Like we want to get a result that is very fast and it is accurate. We don't want to spend a lot of time running models that would actually not give us the right results. So because of this, so people don't, like researchers so far haven't used the bin parameterization, but they've used the bulk. They are using it and they'll still continue to use it until they actually like get the bin, like find a way to actually like reduce the terms of computer time and memory. So when you want to actually like choose, like use a microphysical parameterization. Okay, now that we know we can use bulk microphysical parameterization. Okay, so how can you like represent, how do you know this is the right thing to do to represent the snow? So the first thing you need to do is to know the snow geometry. That is, you know how the snow looks like, the shape, you know the density of the snow, you know the diameter, you know the mass of the snow particle, because actually like in different layers of the snow, there are like different densities involved. Like in the course that I took in January, like in the field work that we actually had, there was this part of like, we were measuring densities for different, in the snow pits, we're measuring different densities. Like we said that the density at the top of the snow was different from the one at the middle, and it was quite different from the one underneath. So these are the things that you need to consider. You need to know the geometry of the snow. You need to know the particle size distribution, diagnostic method, and you need to know the shape of this method. Would it be like an exponential distribution? Would it be a gamma distribution? Those are the things that you need to know for you to be able to say that, oh yeah, that this, I can actually like parameterize my microphysics properly. So now, as I earlier established about the suspension mode and the turbulent suspension, the saltation, all of that. So here we'll be talking about the mathematics involved. So in the atmospheric boundary layer with blowing stone, like the primary transport mechanism for aeration and transport and deposition of snow is saltation and suspension. I earlier said it, that is like, those are like the two. We saw that the other one was not very useful for a blowing snow model. And there's no way we want to measure the transportation of something that is not moving. So the repetition doesn't really work. So it's the equation of state that can be used to describe moisture is in this equation. So in this equation, we have delta Q, delta T plus this. This actually like explains the advection part of the program. Then we have this term which is equal to this. So it's the delta Q is like the total specific humidity of air, and it is measured in kilogram water per kilogram air. Uj is the velocity, and we have, you know, the T is change in time, the X is change in space, and SQT is like a source term. So this QT can actually be divided into two, like the vapor and the non-vapor. So the vapor part is like more like the liquid part, like the gaseous part of it, and the non-vapor part is like more like that tends towards the solid part of the total of the specific humidity of air. So when we go to Q, we speak about the vapor of the specific humidity of a vaporized air. When we talk about Q, we'll talk about the specific humidity of non-vaporized air. So we are just like I said, SQT is the moisture source term, and we assume that the snow grain have the same size, just for general because we go deep down into having other ideas that it has different sizes and all of that, then the equation becomes different and difficult, and like we have a lot of dimensions and all of that to consider. But this is just like the simplest case, which is we assume that they have the same size. So the balance equation can be replaced with equation. So this is the equation 3 is the balance equation. And we see that there are some similarities between equation 2 and equation 3, just that the right hand side is kind of different from that. And in this right hand side, we have the humidity that is multiplied by the velocity, and also we have WF, which it represents the velocity of free fall. So what happens in this right hand side is the same as what happens on the left hand side, but we just have understand like different ways that it has been parameterized. So in my computing artifacts, I'll actually use this equation 3 to form different like case studies. So I'll be having 3 different cases. I'll be having a case of solving the right-hand side, the left-hand side equal to 0. I'll have the right-hand side plus a diffusivity term, and I'll have the right-hand side diffusivity term plus a disturbance term, so which I'll be showing you shortly. This artifact was, so I'll be explaining, like writing out the math in Galicki method and explaining, like showing the convergence study of this. That is, okay, if does this math work? Like, is it correct? Is the solution obtained? Like, are the solution obtained correct? And what do they like represent? So the machinery used to solve this equation is found. If you want to know more, read more, there is this book, Introduction to Element-Based Galicki Method, and it's following what I'm doing in the special topics class, Math 597. And if you find it very interesting, you can actually like register for it next fall and like that too. So my computing artifact is here. Yeah. Although I'm not going to like show you the codes that I have now because I am still working on it. I'm not like done, but I just like have like the summary of whatever it is I want to explain to the house regarding this. So just like I earlier said, that we have we are going to be explaining like 3 processes. And I said in 3 cases, we have the transport equation, the basic advection equation. I just tells us, okay, we have a change in time term, we have a change in space, and it's equal to 0. Then we have the diffusion. Like on the right hand side now, we don't have 0 again. We have a diffusivity term, then the diffusivity term, then we have disturbance. So these are just like definition of terms and all of that. So based on what I was obtaining, okay, so for this right here, I was trying to get if a check, one of the checks that I did was to get if the diffusivity term, this V that I have, this V, that if it is equal to what was obtained in the like if the parameter they gave was actually like correct and what's like what I obtained was the same as what they obtained in a book, and in some of the texts that I actually like read through, and I saw that true that it was like the same. And it was actually when I actually like when you come for the exam proper and you see like what the codes, or you see like the plots, then you would understand what I'm saying better. But it actually like it matches what's the exact the idea of the exact diffusivity term should be. So we had the idea that it should be between a specific range of numbers, and just like doing the normal calculation with the assumptions and everything that they made, I actually like got those stuffs right here. So that's all I'll be showing you about the computing artifact for now. Yeah, so now we have the snow model description. So how do you like understand that when you see a numerical method and a numerical model and you say, oh yeah, this is a good, this could be a snow model, or this could be very useful. So numerical, I earlier established that snow actually like contributes a lot to the climate. So we should know that snow models like compose most of climate models. Like since snow contributes to the climate, so snow models too, they are also like climate models too. So the aim of the snow model is to develop a model for specific applications that you want to know what you're using it to do at this time, or at the specific topography, the specific height or something. So the primary task for the numerical model is to compute the time and space evolution of variables, just like we saw in that equation 3, in that we had a time variable and we had a space variable. So when we want to model this for snow, so we should have something like that has a time dependent, space dependent, and also it should be characterizing the snow conditions and its interaction. It should talk about the atmosphere, putting in cognizance the atmosphere, like vegetation, and everything should be expressed like in mathematical equation. So the model needs to account for one, physical processes operating within the snowpack. So in as much as you are building a math, you're writing math equations, the model should be able to capture the physical processes operating within the snowpack. Is it like what's happening with temperature, what is happening with the humidity, what is happening with less specific heat or something like that, depending on what condition that you're speaking about on the snow. And also you should have initial and boundary condition. Okay, I forgot to mention that in my computing artifact, I will actually be using two types of conditions, boundary conditions. I'll be using the periodic, I'll be assuming periodicity, like periodic conditions, also like the Dirichlet condition. And the periodic condition just entails like you have like, let's say from between 1 and 10, I know the value of 1 and the value at 1 is equal to the same value at 10. So that's just like assuming that. And also for the Dirichlet condition, it's just like you have like that one to like at a specific value of Q at 1, there's a value there and you have another value also there, which doesn't have to be like the same thing like I earlier explained for the periodic condition. So it says contains, because this concern measure the energy and mass balance at the interface between the snowpack. So it deals with like what happens at the beginning of the snow model, and also that what happens like at the edges, at the domains that we have. So the examples of snow models that I actually like out of the papers that I read, they spoke about some models and all of that, but there were like 3 models that actually were very, very interesting and very, very useful and current and like was like numerically involved. So we have the snowpack. The first one is the snowpack, and this snowpack was actually used to develop two more models, like couple 2 more models, which we'll be seeing shortly. The snowpack is a high complexity snow cover model, and it's developed from SLF in Switzerland. It's not a US-based model, and it is used for predicting snow development with fine stratigraphic details. So when we talk about stratigraphic detail, we are talking maybe like say the hardness, when you touch it, how hard is the snow? We're talking about how wet it is, like what is the grain size and all of that, enabling snow stability estimations. So the core snowpack model, it solves the heat equation using a finite elements mesh. So for as many that has done something that relates with finite elements, you actually understand how this works. Like we're having heat equation, we are solving it using the finite element matrices, which involves with mass changes of ice and snow to preserve the layer. So why they use this finite element implementation is because it is valuable in describing the various snow stratigraphy as the snow is changing with in size, grain, in wetness, in hardness, and all of that. The finite element implementation actually like makes it very easy for them to like describe all of these things using different boundary conditions and for them to get very nice stability. So in 2006, this set of people, Len et al, his group, they actually formed another model called Alpine 3D. So the Alpine 3D was actually like used coupled with the snow models and the snowpack model. You would be seeing that shortly, and it was very useful for investigating mountain surface dynamics. Just like I earlier established when I was explaining the classes of snow, that is explained the tundra, the maritime, alpine, and all of that. You will see that from the name of this is like alpine. Alpine is talking about places that are mountainous. So you will know that this model is going to work for mountainous areas. So this mountainous 3D is like a 3D mountainous model that is used for avalanche warnings, for permafrost development, vegetation changes, like just like the event, just to investigate how snow cover works and changes with, let's say, avalanche warning, works and changes with vegetation and all of that. So this model, and most of this model actually is, it has to do with computation. Just write small math, and the implementation is the big deal, because you need to know what it's like, just like once you've gotten the boundary conditions right, you've gotten the topography right, yes, then you need to know, okay, under at what conditions would be useful, and under at which condition it wouldn't be. So this Alpine 3D consists of two structural units, like the input and the output, and the computational part. So the input is just like what I've earlier said about, like, the data on topography, the vegetation, depending on what parameters you're interested in looking out for. Then we have the computational part. Let's say when you now, let's say, run a code, maybe for a few days, then you get the outputs, then you start visualizing what you're seeing. So this is the computational part consists of three modules. We have the snowpack, the snow drift, and the energy balance. So, earlier we established that the snowpack was a very useful model. So this Alpine 3D is one of the models that we use the snowpack to actually like build. So it's like a combination of three models, and here we have Alpine 3D. It says the one-dimensional snowpack model was previously coupled in an offline setting. So using this Alpine 3D, the snowpack model was actually like coupled as an offline setting, in the sense that it just for like, it was like in the previous version of snowpack, and it was just used with there's a behavior that snowpack had maintained as an offline behavior, that you can use it on or without like the computer. So it says with a three-dimensional solver in the atmosphere, specifically for snow transport and spatial description of snow. While in an online approach, so we use snowpack with WRF. So there's this new model that was developed last year called CryoWRF, and we use snowpack with WRF. WRF is like weather forecast to research model. Like, it's one of the models that I've been in for like 2 decades and before then. So more than 2 decades now. So we use this snowpack in an online setting. So, the way it was incorporated, this CryoWRF was incorporated, they have to run the snowpack and the WRF together. And this snowpack actually like acts like a land surface model. So when they are coupling like those models together, they need to have like a part that would actually like be the snow, that would extensively speak about the snow. And some part maybe we'll speak about some other parts or variables of the atmosphere, which the WRF actually does here. It says development combines several benefits. So the combination, might be wondering, why would they, since snowpack can actually work on itself, work by itself, why should they actually want to combine it with other ones? So it's because when you use those the two, like the packages together, it's actually like useful for like domain nesting. It is useful for multi-case capability. That is, you get like the resolution the resolution like you can actually work with. It's like easier like than using like independently, like using WRF to run specifically. The kind of result that you obtain combining the two together, it's much more easier, faster, and simpler than just doing for, let's say, WRF separately or snowpack. It says snowpack allows for intelligent measuring of vertical layers. So you can actually like assume a lot of things here, and it would actually work, and you get very reasonable results. So the significant difference between this coupling method with snowpack is that there's a transition from offline approach to online approach. We saw that in the Alpine 3D it was like an offline approach, and in this CryoWRF it's like an online approach. So we have like, there are various feedback processes that the offline approach cannot describe, that they cannot actually like simplify, that actually this snowpack with WRF actually does in CryoWRF. So we have several limitations of snow models based on the paper that I've read. The identification of the right choice of topography is one of the problems. Like, you don't know at what specific height is good enough how do we account for the errors, like, and map out so that, okay, so let's say, okay, we want to actually look at a specific place, a mountainous area. Okay, so what is the idea of the ideal mountainous area? What is the idea of where should the mountainous area be? Like, if snow falls, let's say for instance, snow falls on Mount Kilimanjaro, is it the same topography as the snow that falls on, let's say, the mountain in Bogos Basin? Is it the same? So no. So how do we like identify the right choice of the topography that we want to consider? Then another limitation is the lack of reproducible results. So I've tried some of these things. Some of the papers I read, like, I tried as much as possible to like, let's check if the results would be producible or not. But so most of them did not even give enough explanation on how they went about. They just brought out their solutions and started explaining with little or no explanation of how to get those results. Furthermore, there is also the problem of computationally expensive and time consuming. Some of these models you as just like individual, if you try to work on this project, on like you produce some of those models, it would actually like take you longer time, and also take you like you would need more computational support than the way they actually like present it. So like, for example, this man in 2016, Sutter and Gallows, in their work found a better approach to use like large eddy simulations, that's like a fluid dynamic term, to resolve boundary layer advection problem. But the model, they couldn't do much because of the computational costs, that they had plans to do better things at different heights, at even higher heights. But because of the computational cost and the numerical stability, they could not do much. So some of the models actually have this kind of problem. And also there are a lot of assumptions made that about the size and the shape. Some would just like assume that, oh yeah, let us, because somebody used it in this one, so this is like a good guess, so let us just use it. And this guess could actually be wrong or true, and it actually like affects the efficiency of the mass and energy exchange, because when there are errors everywhere, the efficiency just kind of like get affected. So I have this open research question that I don't know if you have any contribution to what you can also give answers to. Okay, the first one is like, how do we determine the correct values of parameters to you? Like, how do you know, like, just like I said earlier, that most of these no parameters, they just get values for like, oh, okay, let's just decide, let's just assume that this is this, let's just assume this is this. Does this assumption, like, does it affect the accuracy of what we have? And also, even if it does affect the accuracy, so like under what conditions is that when we want to assume that this specific value is for this, what conditions would they hold? And does the global warming affect the snow model accuracy? That is the model that was, let's say, established, like the Alpine 3D, established 2006, and with the present condition of the global warming, and now that if we want to use it again, does it affect, like, what has happened then and now? Does it affect the model's accuracy? And also, how do we account for all of these errors that we have in this? Like, is it only, apart from the measure of dispersion, can I just see like a model and just say, oh, this is wrong or this is right? Even if it looks right, how sure am I that it is right when I actually like make use of the result? From the results, let's say the graphs that I've seen based on it, how can I know that it is right? And also, how do we choose a specific snow model based on the amount of snow we get in a study region? That is, how do we account for extreme situations in snow modeling? Like some years now, there will be just high amount of snow. Some years there will be low amount of snow. So how do we account for this in the snow models that we have? So these are like the open questions that I have, that I don't know if you have any answer, you can just like pen it down. And that's all. I want to appreciate my supervisors, Dr. Cooper, Dr. Flores, for their help so far, and also my appreciation to Yao, Gaunzo, and Ibrahim Alabi for their help during this ride home. Yeah, thank you for listening.
Thank you very much, Yemi. Now it's time for questions and comments. Please, in case you have any, just unmute and pass it on.
Yeah, Yemi, hello? Hello?
Hi, I'm here. I'm here.
Yeah, okay, sure. So, thank you for this presentation. I just have some feedback and some comments. But the first thing, I'll start with the question. At first, I don't know which slide was that. You mentioned about the bin parameterization, which hasn't been implemented. So how did you get it into your artifact if it hasn't been used?
Oh yeah. So in one of the papers I reviewed, and that is, I'm coming, that is this, yeah, in this explicit forecast of this one, this Thompson's paper and this one, they spoke about microphysics, like the parameterization, like the beginning, the background, and they gave, like they said, they gave the explanation that they have two, but most people don't use this one because of this and that. That is why, like they just explained why they use the bulk microphysics, like why it is popular than the other one because of this. So that was, I got it from my paper.
Okay, thank you. And maybe again, just maybe I got lost somewhere because
Okay.
it tended to transition from the artifact. It's like you went into the artifact and you went outside the artifact in the middle of the presentation.
Okay.
So I failed to connect between the two, if you continue the artifact or it's your work after the artifact.
Okay, you were asking if I should, okay, you were saying that, okay,
yeah,
I should put the artifact like at the bottom of the presentation.
Yeah, that's how it feels.
Okay.
I think that's the right way. Maybe put it at the end of your presentation so that people don't get lost where it's like that artifact, it's your work.
Okay.
Not really what you're synthesizing in the from the
At the
papers.
end
Yeah, because it felt like you are coming from the
artifact and
actual,
okay.
So people feel like after the presentation, after the artifact, that's your work.
Oh, shoot. Okay, so I'll give the presentation then. Yeah, okay, thank you.
Yeah. And I don't know, somehow along the presentation you criticize some author. I don't know if it's a right way to do. Maybe I would advise, maybe just say that they didn't mention this, they didn't implement this.
Okay.
Yeah. And I don't know, maybe since you'll be presenting on Zoom, this is just the feedback. I don't know if you feel like you can take it or not, but I feel like the slides are more, they're heavy text, which might be easy to lose the audience. Yeah. I think that's what I have for you now. I don't know. Yeah.
Thank you.
Yemi, when is your presentation, the final?
Next week, Friday.
Next week?
Yeah.
Oh, you still have some time. Yeah, because my comment was going to be kind of similar to what Katrina said. There is misconnection from where you started to the end. And also the words you are using, I'll also say you do the same thing as what I said, Sandra. If you can record yourself and listen to yourself, you'll easily spot some things that you would like to change, like the flow of the presentation. It just get disconnected somewhere. So yeah, otherwise, did a good job. This is a lot of things.
Okay, thank you.
My concern would go actually to just adding on what Kachinga said. I think there is a lot of text.
Okay.
Sometimes I feel like people have to follow what you say, at the same time they're distracted by what you put there. If it's a lot, I'm tempted to read, and then I end up missing out on what you're saying.
Okay.
I think, generally, that's it. And then I don't know, the timing was also not right. I felt somehow that you repeated some things like several times, and it would be a good practice if the meeting is recorded, Titus will send you the recording so that you can listen to yourself
Okay.
presenting. Yeah. If you have more questions, please push them in.
Hi, Yemi.
Hi. Brian.
Yeah, thanks for the good presentation.
Thank you, Brian.
Yeah, I have a question about the microphysics.
Okay.
So are these, you said you're using WOF, right?
Yeah.
Are these schemes implemented in WOF, or they are things you did by yourself in your artifact?
For the microphysics.
Mm,
In WOF, we have different test cases depending on what you want to run. So we have like real
okay.
cases, we have ideal cases. So also it has like sub things that kind of, okay, I would actually explain here. So in like the real cases, like you're running real life data, we take like a specific like location. Let's say we are running from places like, let's say Texas or Florida or Colorado or California, we take like, we run based on like using their what's it called, the latitude, longitude, the location on the map. But for the ideal case, it's kind of different because you are just like idealizing it. So this microphysics actually like comes like packages in like WOF, depending on the kind of test case that you're working on. If it's like a mountainous test case, like AO2D test case, if it's just like sea breeze, if it's like tropical cyclone, it depends on it, on the specific, on what the specifics, like what you're actually like looking out for, like the kind of combinations that you would like. And that actually like determines also what type topography those like test cases would be. Does that answer your question? It sounds more complicated.
No, because you're saying it basing on the regions. But earlier you were saying that it depends on the prognostic variables. For example, the snow depth and all those kind of things.
No, what I'm saying here is not, okay, I think you're mixing. I was talking about WOF. Like for you to specifically speak about which microphysics is you need to know, like that, those are like the basic things before you know, okay, before you said, okay, you want to use WOF, like you need to like know what you want to do yourself. Like, okay, if my test case is going to be, let's say, like tropical cyclone, am I using like tropical cyclone microphysics for which location? Okay, let's say you don't even have a location, you just want to like just run it arbitrarily. That's like the ideal case in like a package, like a model like WOF. Then when you get to the tropical, so this test case, you will see the microphysics packages that speak about the density of the snow, just like I earlier explained, like that those are like the microphysics packages inside. So the basic thing is for you to first know like where and what like you are doing, then before you start getting down into the microphysics. Does it answer it, or it sounds more complicated?
No, you answered.
No?
Thank you. I'm saying thank you.
Okay, so Yemi, about the open questions.
Yes.
So I'm wondering if the papers you reviewed said anything about it, like not necessarily do it, but maybe at least might have said something about it or suggested some solutions, or if you on your own like have some ideas about those open questions.
For some of the open questions, well, some of the open questions to like, I got some of these ideas from reading some of the papers, and some were just like some that I'm actually like encountering in my research presently. Like I'm trying to like find answers to that I haven't gotten right now. So I can't really say that I have specific like ideas to how to like answer them. So that's why like I'm presenting it like maybe from my point of view, I cannot see it. I would like you all to like contribute in that regard.
Okay, so but did any of the papers by chance suggest anything about these open questions?
No, I had those questions in my mind while reading those papers, like because they did not give answers to them. And there was even one that I even gave their own open questions to based on what they were doing. So which was just out of it. No, they just wrote their paper, they drew their conclusion and like that. They did not like, it was just based on maybe where I was thinking way too far or too much about the whole combination of stuff to bring out this.
Okay.
Olayemi, about those questions, who is supposed to answer them?
You guys
Sorry,
are supposed to answer, not me. I'm the one.
I mean,
presenting the
no,
question.
but the presentation won't be us, it will be professors. I'm saying professors are supposed to answer this.
Okay, professor. Yeah, but you are the professors for today. You are the one. Yeah,
Okay.
yeah. So
Sorry, Titus. I hijacked your talk.
Yeah, it's fine. Okay.
so Titus too. You can just pick a number that you would like to answer. Thank you.
No, but this is related to your research. So potentially these open questions. I think if you have open questions or if you identified gaps in your comp exam or like in your synthesis, that could be a potential question that you may want to answer in your proposal or something. So, like, because yeah, of course, if you're saying we have to answer it, that's okay. But at the end of the day, people have different research areas.
True.
I'm not
Yes.
sure. I'm not sure I'll be ready to answer this one when cosmology questions are not answered.
True. Yeah, sure.
So there is no any existing research that answered these questions? Because for
No.
me, they sounded like these are, if I was a professor, these are the questions I would be asking you.
Yeah, that's the point. So before I was asked the question, I would just present it out. You get, it's a counter reactive method. Sure. I'm the first person asking, so who gives the answer? Yeah.
Seems like we have exhausted.
Yeah, I have a question.
Oh yeah, Stanley, you're welcome.
Yemi,
Yeah.
did you do any like work simulation in your artifact?
Did I write?
Did you do any work simulation in your artifact?
No. It's Gaelic methods, MATLAB kind of stuff. Yeah.
Okay.
Yeah.
Okay then. Then there's really to ask.
Oh, okay.
Yeah.
I can see you under the camera.
All right. In case there is no any other question, thank you, Yemi, for the presentation.
Thank you for having me.
Wish you the best.
Yeah, thank you.
At this point, I want to invite Titus to talk about some information.
Okay.
I think he actually is supposed to pass on some info to us about Siam generally. Titus, you're welcome.
Okay, thank you. So I think on Friday we'll be having our social event. So the social event was supposed to be today, but we had to do some little changes. just to make sure that everybody whose comp exam is due in some few days will have the opportunity to talk as well. So we are scheduling our social event on Friday. So we'll be sending an invitation soon. So we hope to see all of you there. Yeah, I think basically that's just the announcement I have. Thank you.
Thank you, Titus. Kachinga, any other business?
I think there's none. Yeah, I think it's just a social event is supposed to happen. Maybe others will be communicated to through the week. Yeah. And maybe just is it the executive meeting, the officers meeting at 4 p.m. Yeah. Yeah, I think that's all.
All right. Thank you. Back to you, Titus.
Yeah, so I think we'll just end the meeting here. Thank you guys for coming.
Thank you, everyone.